Greetings and welcome everybody to Chapter 2, Lesson 2-3, Solving Multi-Step Equations. So today's learning targets are as follows. We are going to solve equations involving more than one operation. Additionally, we are going to solve equations involving consecutive integers. Now, you will know that you are successful when you are able to determine the value of unknown variables in equations involving integers and fractions by performing inverse operations. Also, you will know you are successful when you are able to prove your proposed solutions to the unknown variables in equations involving integers and fractions by substituting them back in to the equation. Interesting stuff, guys. We are going forward on our path toward mathematical enlightenment, but let us keep these key questions in mind, for they will serve as our guide. The first of which is, which operations in the equation must be undone? Very key question there. How can you use variables to represent consecutive integers? How do expressions for even and odd integer problems compare? Keep all these in mind as we go forward, guys. All right, so without further ado, let us proceed on to the meat of this topic here. So, hold up, there we go. Okay, so let's see. Anyways, like I was saying, our whole goal, solve multi-step equations. Here we go. Equations which require more than one step to solve are indeed known as this word here, multi-step equations. Okay, so let's see, consider the following equation, this one right here, guys. So now you may be intimidated by how to start. You may not know where to start. But here's the thing, though. I would recommend you you locate the side of the equation with the variable on it. So in equation there is two sides. This is one side, this is the other. Direct your eyeballs to the side on which the variable exists first and foremost. It happens to be, in our case here, this side. Now, once you direct your eyeballs to that side of the equation, and always keep in mind the goal here that you want variable to equal something, right? That's supposed to be a box there. Box. There we go. Variable. Keep in mind this is the goal. Variable equals something, anything, whatever it is. We don't know yet. But with that in mind, and looking at this, you will perhaps notice there are two things happening to the variable. Happening to the variable. Okay, and these two things, we'll get more into it, but these two things happen to involve this 5 here and this 2 here. We'll get into it here in a second. But alternatively stated, you can say that the variable has undergone two distinct transformations. And I am very particular with the word choice I use here, transformations. I use that because in algebra you will work with this idea of transformations, and not just algebra, but beyond algebra, algebra 2 and calculus and so forth. So I am sort of getting your senses, I'm getting you to have a sense for these higher level terms here. So transformations. There are two transformations happening to this variable. So let's talk about it. It doesn't matter which one we start with, but let's look at each one independently. So let's look at transformation number one. And I'm going to go ahead and say that transformation number one, again, doesn't matter which one you label as one or consider to be one, but I'm going to go ahead and say that there is a value of 2 being added. All right, so the plus 2 here. I'm going to go ahead and say that's my transformation number one. There's a value of 2 being added to the side of the equation with a variable on it. You will need to perform the appropriate inverse operation. Now, hopefully, from the last lesson, you remember what this is, right? What this is. Essentially, inverse operations, a very key, important thing to understand about mathematics in general. Inverse operations mean, to keep it very simple, it means do the opposite of what you see. So, 2 being added, got a minus a 2, so forth. We'll get more into it. But essentially, all right, we perform inverse operations, the appropriate one, in order to eliminate, oh, I misspelled that there, eliminate. There we go. Spelling's not my, it's not my thing, guys. All right. Eliminate it and transfer, let's see, transfer it to the other side of the equation. That's exactly our purpose. All right. So what am I talking about? How do I perform the appropriate inverse operation? Well, it's not super complicated, right? Well, I'm going to guide you through here on this little example here, okay? Let's see. Well, essentially, here's our equation that we started with. So, to perform the appropriate inverse operation, again, do the opposites. So this plus 2, I'm going to do the opposite of it, minus 2, for the purpose of eliminating it, and therefore transferring it to the other side. Now let's see, if I kind of go vertically here, 5 plus or minus 0 happens to still be 5x. Okay, plus 2 minus 2 happens to be 0. Now, I'm not going to write 0 in math. We just tend to not. So I won't explicitly write it. Okay, 12 minus 2, 10. Okay, and then we divide 5. Well, actually, yeah, I'm not even going to, I'll save that for the next one here, right? But we have successfully at this point performed one step of our multi-step equation. We performed one step. We took care of, you know, transformation number one, basically. Now, again, I said there's 2 steps. There's 2 transformations to consider as to what's happening here. So, with that, let's talk about the other. Let's talk about the other. Okay, so transformation number 2. Transformation number 2. And we already took care of the 2 being added, so let's look at there is a value of 5 being, right, we had 5 in this, that was what we had, plus 2 equals 12. This here, if, this indicates this coefficient, you'll learn this term later, coefficient next to a variable indicates, there's nothing in between, but it indicates that multiplication is happening. So we have a value of 5 being multiplied. Okay, so you could little x there, or even a little dot there indicates multiplication, or even nothing at all. But we have 5 being multiplied to the side of the equation with a variable on it. And just as before, you will need to perform the appropriate inverse operation in order to eliminate. Again, I'm very peculiar about my word choice here. Eliminate. In algebra, you will see this term once again in a very specific context. And I think you're going to like it when we get there. But I'm very particular about my word choice. So eliminate it and transfer it to the other side of the equation. And once again, I'm going to highlight inverse operation because it is so fundamental, so critical in math that you understand what it is and how to appropriately perform them. Again, it bears repeating that inverse operations, IO equals do the opposites. Do the opposites, right? Highlight that as well. That's how fundamental, that's how critical, that's how important it is that I want to repeat myself when we talk about it. So let's see. Now, when I deal with this 5, I've got two approaches I can take. I've got two options here. So I can talk about both here. I'm going to talk about, let's see, the transformation. I've got two options. I can deal with the 5 here as step 1. Remember how I took care of the 2 as part of my first transformation and my step 1? I do have the option here of doing this as my step 1, but I also have the option of doing this as my step 2. Now I'm going to go through both here and give you sort of my recommendation and clue you in as to some of the, I guess, pitfalls or complications that result in choosing one or the other. So let's talk about, let's consider if I want to handle this 5 as my very first step. You can do either one, the 5 or the 2. It does not matter. The results, you will get the same thing. Now, with that said, let's try it. Let's see here. I recognize that, as I said earlier, this 5 is being multiplied by this variable. So, doing the opposite, performing the appropriate inverse operation, to do the opposite here, I would need to divide. I would need to divide by 5. I would need to divide by 5. In fact, I would need to divide 5 not just on this term here, but I would need to divide 5 by every term on the side of the equation for it to work out appropriately. So divide everything by 5. And same thing on this side of the equation as well. Divide everything by 5, for if you do not, you will end up with a crazy incorrect result. Now you may remember from the properties of multiplication and the properties of division that when you divide 5, you are also, right, dividing by 5. Let's see here. Dividing, dividing by 5 is the same thing as multiplying by its reciprocal, the reciprocal of this 5 on its own, right? So, um, you can sort of leave it. This may be easier to visualize maybe than doing the reciprocal, but if you did the reciprocal, you would do the same thing. Just, set up your reciprocal, brackets, 1/5, and distributes. So that may be, I don't know if that's easier for you to visualize, but I'll stick with this here. This visualization tends to resonate a little bit more with students. So 5 divided by 5 happens to be 1, and I have x there. Now, we don't generally write 1 of an x or 1 of a variable, so I will just leave it as plain old x. Here I've got plus 2/5, and here I have equals 12/5. Now, the nice thing here is that all these denominators are the same, which is wonderful. That means, if I wanted to finish this equation out and actually solve it and get an answer, that would mean I can go ahead and subtract 2/5, and I shouldn't run into really any issue again because the denominators are already common. So 12/5 minus 2/5 equals 10/5. And if you were to reduce that or understand that this really means 10 divided by 5, that equals 2. So this equals 2. So that is the result you get by taking this approach where you deal with the 5 first. Now, let me show you the other approach here. You can look at it as the second step that you do, or the second transformation that you undo. So let's see. So if I were to do it as the second one, I would first need to get rid of this 2 like I did above. Okay, let's see, get rid of that. Hold on. There we go. Okay, so 5x equals 10, just like we had before, and then divide everything on this side of the equation, which just happens to be this one term. Divide everything by the 5, divide by the 5, x equals 2. So let's see here. Let's think about what just happened here. I have a 2 and a 2. The result, guys, is the same. The result is the same. They are equal. The result is the same. So I want to point out you can do, you have choices as to, in this particular case, as to which step you want to do. Now, here's what I recommend though, okay? I recommend you deal with the 5 as the second transformation, or in other words, when you're solving these multi-step equations, I think it's easier and I think it resonates more if you take care of any sort of term that is being either added or subtracted. So in this case, we had the plus 2, 5x, or we had 5x plus 2, and then, or if it was 5x minus 2, I recommend dealing with terms that are being added or subtracted to the x term first. It just is easier. You don't have to, if you aren't careful, you can potentially not divide everything by 5, in which case you would get x, and then plus 2 equals 12 over 5. That's completely different. That would get you a completely different answer. And I see that often. So to potentially avoid some pitfalls and mistakes and errors and complications, it's easier to visualize, dividing or, you know, one term on this side. So again, you have the choice, but I recommend dealing with addition and subtraction first before you consider undoing, before you consider doing the inverse of either multiplication in our case here, or let's say if it was x over 5, if it was division, undo that. So do the addition and subtraction before you think about undoing multiplication or division. That's my recommendation. So let us let us basically we got more to do. We got more to do. Let's just get a bunch of examples under our belt so that we can become really proficient with this stuff. So here we go. Here's a couple more examples here. A couple more examples. All right, let's look at this. So here's an equation that happens to appear before our very eyes out in the wild. And as I said, I like to look at terms that are, I notice there are two terms, okay, here on this side. There's one term here. I also notice this is the side on which the variable happens to reside, right? There's my variable here. So this is sort of where my eyeballs go right away. With that said, as I said moments ago, I want to look at the terms that are being subtracted or added first, remove those, perform inverse operation on those in order to make my life easier and avoid potential pitfalls. So that's what I'm going to do. I'm going to perform the inverse operation here first. So if I do that, 11x and nothing happening to it results in 11x minus 4 plus 4, that's 0. Okay, and then 29 plus 4, that happens to be 33. Okay, there we go. That was, I'll call that one step, right? Because we're this whole idea that we have multi-step. So that was actually that was one step. That was the step. The second step happens to be the undoing of this multiplication that's happening here. The undoing of it. This here is step 2. The act of undoing the multiplication through division. So let's see. 11 divided by 11 happens to result in 1x, or simply just 1. This here, 33 divided by 11, this comes out to be a 3. Okay, a 3 here. Well, again, don't take my word for it, for I insist we prove that what we determine x to be is in fact resulting in a statement of truth. Equations are all about statements of truth. 1 equals 1 is an equation, and that is indeed true. Right? Our whole goal is to get some number, some value equals some value. So let's see if we can get that. We want both sides to be equal, for that is what a statement of truth is, and for that is what will tell us if our variable that we solved for is indeed correct. So let's see here, 11 times 3, that is 33 minus 4. I'm not even looking at this side yet until I get this down to a single, as much as I possibly can. So let's see, 33 minus 4 happens to be 29. Okay, now I can look at this side. Well, let's see. There's only one thing here. I can't do anything with it, so I'm just going to keep bringing it down until I get to the very bottom here. And guess what, guys? 29 does, in fact, happen to equal 29. This is resulting in a true statement. This true statement is the outcome of the input that our x variable was 3. So it's true, it's correct, everything checks out, we are good to go, we know that what we did was correct. Let's talk about this one. Now this one here, you may notice here that, or maybe your first thought here is that, hey, wait a minute, you told me that, you take care of the addition first, and that's the recommended approach before you think about undoing multiplication and division here. And yes, you do definitely that. You heard me correct. However, perhaps I was not clear when I was stating that before, is that yes, there are two steps, and you need to do two different things to it. But the reason why you had the choice in the first place, remember, here was the equation from earlier, 5x plus 2 equals 12. The reason you had options in the first place was because you had two separate terms to deal with, right? Each thing, just a refresher, each thing in between an operator in an equation is a term. So this is term 1, you can say term 1, term 2. Okay, in this case, in this equation here, we don't have that thing. All of this, there is no operator between something. This is simply a, a term itself being divided. There is no plus, there's no 1 plus anything or some sort of separate term. This is simply a one term equation with one term on each side. So because of that, you really have no choice as to the order of the transformations you select. Your only option here is to begin with the, following the order of operations, following PEMDAS, following the larger, I'll call it the larger shell of really what's happening, the larger shell of what's happening. This is a single term, and really what's the bigger skeleton of what's happening here is that there's a thing. Don't get confused here by this. This is simply a value. This is a number or something over divided by a thing. This is just simply division. That is the larger picture of what's happening with this term here. So really, your only choice at this point is to undo the division that is happening. So you must begin with multiplication. You do not have a choice here because it is one term. So let's do that. Let's do that here. I'm going to, when I undo division, via multiplication, I always put both sides of the equation in brackets. Okay, I do that for a very deliberate reason, and you'll see that here later. Anyway, so uh, times 8 to both sides. Okay, if I times 8 to both sides, essentially these 8's cancel, or they cancel because it becomes 8 divided by 8, which equals 1, which in math we don't tend to write 1. That's why they cancel, right? That's why they cancel. Anyways, so they cancel, and then all you're left with is a plus 7 equals, now I have 5 times 8. Let's see, 5 times 8 here. That happens to be 40. Okay, now I have undone the multiplication, which resulted in two terms here. Now, our whole goal is to get a by itself, a to equal something. So I don't really have a choice. I can only really do one thing to make that happen, and that is to inverse this plus 7. Inverse that. So let's see, a becomes just simply a, which is exactly what I want. 40 minus 7, 33. Let's prove it, guys. Let's prove it because don't take my word for it. Don't take the calculator's word for it. We prove things. We prove things, and when we prove things, we become enlightened. So 33, substitute that in. We're redoing the equation, substituting the letter for what we evaluated it to be over here. So 33. Okay, so again, I'm not even looking at this side until I get this all down to one single thing, right? So let's see here, 33 plus 7, right? Order of operations says I need to, there's an invisible parentheses here. I need to kind of get this simplified first before I worry about what's happening outside of it. Outside of it would be all this business here. Anyways, 33 plus 7, 40 divided by 8. Okay, perfect. So now this is down to single numbers, and there's a division happening. So 40 divided by 8 happens to be 5. Okay, now I'm going to direct my eyeballs over to this other side. Let's see here. Okay, there was one single number here. There's nothing to do with it. So I'm just going to bring it all the way down to the very end. Oh, look at that, guys. 5 does, in fact, equal 5. Therefore, this is a statement of truth. Therefore, the truth of the matter is when A was 33, that was correct because it resulted in a true statement. Perfect. Let's look at the next one, guys. Let's look at the next one here. There we go. All right. This one here. Okay, let's see here. Got a 2a plus 6 equals 4. Well, addition and subtraction, let me deal with that first. As stated before, 2a, this becomes 2a. This becomes, let's see, minus 6 plus 6, that's 0. 4 plus 6, that's 10. Okay, 2a, multiply, this is multiplying here, so undoing it. 2, 2, let's see, a equals 5. Excellent. Let's plug it in. Let's substitute. Let's check. Let us prove the statements and hypotheses we make in this world. All right. So now, again, don't look. All right. So let's see. 2 times 5 is 10. I have a minus 6 and equals something. I don't even know because I've crossed it out. It's not there in my imaginary world here. Okay. 10 minus 6 happens to be 4. Okay, now let's see. Let's see here. Oh, this is a single number. Bring it down. Let's see, bring it down, and 4 happens to equal 4. Therefore, this is a true statement. Therefore, the missing value, the variable we substituted, happens to result in a statement of truth. Therefore, we know A happens to be 5. It is correct. Let's try the next one, guys. We're just rolling through here. We love math. We are doing this thing. We are becoming proficient, and we are happy that we are. All right, let's see here. So very similar to before, this is a single term. I have no choice but to undo the division first. So allow me to do so. Allow me to do so. So undo division, I'm going to do so through multiplication. When I multiply, I wrap both sides of my equation in separate brackets. Again, you will see why later. All right, so anyways, so these cancel. Again, why? Because negative 2 over negative 2 happens to result in 1, and we don't tend to write 1 in math, so they effectively cancel. This leaves us with n plus 1 equals, let's see, 15 times negative 2 happens to be negative 30. Okay, let's see, now I have minus 1, n equals minus 31. Okay, that that I can deal with. Let's try and prove that out. Let's try and prove that out. Okay, boom, I'm gonna plug this in over here, substitute it, negative, so negative 31. Okay, negative 31, again, PEMDAS, parentheses first, in imaginary parentheses. In the numerator here, let's see, negative 31 plus 1 happens to be negative 30. And I have this divide by 2 over here, and negative divide negative happens to result in a positive, so I'm going to get a positive 15. Now I look on this other side. Okay, there was nothing happening, so I can just bring it on down. 15. 15, positive 15 does in fact equal positive 15. This is true. Therefore, n being negative 31, that input resulted in a true statement and therefore was correct. We did it appropriately. Not too bad, guys. A couple examples under our belts. You know, easy stuff, right? Easy day. Let's proceed, all right? So we're going to move on to something a little bit more challenging. It's the same stuff, but just a little bit more challenging. Why do I say challenging? Because, oh no, here we go. The stuff of nightmares. The nightmare fuel here happens to be word problems. Oh yes, guys, word problems don't go away. Nightmare fuel too, because now we have a fraction involved. Oh man, this is, listen, I know your nightmares are being fueled right now, but hopefully we can turn this into not a nightmare, but a pleasant, sweet dream. So, actually, not dream, reality, because this is happening. This is reality right now. So, let's look at we gotta analyze this word problem first. We have to dissect what is happening and put the equation together. If we get the equation wrong, it doesn't matter what we do from that point forward. Everything else is going to be wrong. So it is absolutely essential that we get this equation correct here. So I'm going to read through this to get a sense of what's happening. Let's see here. He's buying a pair of water skis that are on sale for 2/3 of the original price. Okay. Let's see. Actually, you know what? I'm going to go ahead and skip to the core question here. The core question happens to be, what is the price of the skis? That is the core question of this particular problem. What is the price of the skis? So, well, actually, let me actually, I don't want to skip here quite yet. I do want, that is important, but let me continue reading. After he uses the $25 gift card, the total cost is, I like to build out my equations by first identifying where the equation symbol is, for then I know my breaks and what goes on each side. Total cost is 185. Well, that's simple enough. I'll just go ahead and put my 185 there. Okay, but the core question happens to be, what is the price of the skis? So I need to figure out where in this word problem did it talk about price and skis and so forth. Let's see. Buying a pair of skis that are on sale. Oh, here we go. Original price. Price, that's my variable, right? The question is in relation to how do I solve for this variable? And that's good because, generally after doing the equation symbol, I want to figure out which side of my equation the variable is on. So, original price, P. I'm going to go ahead and use the variable P. Let's see, 2/3 of it, 2/3 of that price. Well, 2/3 of it would mean a multiplication between the two is happening. Okay, interesting. All right, let's see. After he uses a $25 gift certificate. So let's think about that for a second. If I'm going to buy something and I have a gift certificate, maybe mom or dad or grandma, grandpa, somebody gave me a birth certificate or a a gift certificate. If they gave me that, it's not money that I have to spend. So I can sort of remove that from the calculation of what I'm going to spend, the price that I have to pay. So I use a gift card, meaning that I subtract $25 from consideration. All right. So this is indeed the correct equation. Again, this is critical. This is the critical step, for if we get this wrong, nothing else matters. We have to get this right for us to be successful in this problem. Now that we have this though, let's go ahead and start solving this thing. The question asks us, what is the price? So let's get P equals something. That's our goal. That's our goal. So let's start doing some inverse operations to eliminate terms and move them to the other side. All in the name of balance, all in the name of the properties of equality. So 25, that becomes, let's see, I got 2/3 P, this becomes 0. I'm not going to write 0, but just know that it's there. This then becomes, let's see, 185 plus 25 happens to be 210. Okay, perfect. Now let's see, I recognize that 2/3 is being multiplied by P. So inverse operations, do the opposite. I'm going to do the opposite. Now this may, you may recall from earlier exposure you've had with fractions that when you divide something by a fraction, anything by a fraction, what you are essentially doing, or in order to solve it, in order to basically, this kind of looks ugly, to make it less ugly, right? We want to multiply by the reciprocal. For when we multiply by the reciprocal, we end up with a denominator. In this case, this is the denominator. We end up with a denominator of 1 and whatever on top. And from the basic fundamentals of math, we know that any number divided by 1 is in fact itself, right? 1 divided by 10 is in fact 10. So this here, 10 over 1 does result in this. That is why we can, and then, but when we write it, we generally tend to just write the 10, and we effectively remove, I air quote this, remove, cancel out, or simply stop at that point writing the over 1, right? That's essentially, sort of the underlying theory and idea and all that stuff behind everything. You don't need to necessarily, I mean, great if you understand that, but just know procedurally what you must do is flip the fraction and do it to both sides. So flip the fraction, do it to both sides. So let's see, this becomes, if I just focus on this denominator here, this becomes 6 over 6, which itself is 1. This here, this top part becomes 6 over 6, which itself is 1. So let's see here. Let's see here. Let me get more space going here. Okay, so let's see this then. Let's see, I have effectively now a 1p over 1, which again, we don't write the ones in math, so we have effectively now achieved p equals something. I haven't even looked at the other side in a while, okay, because this involves some work here, getting rid of this fraction. Now I have that gotten rid of. That is now actually, I'll write the P. Yeah, I'll write the P over here, right? Anyway, so now let's see. So I got a P, and there was nothing left for me to do here. So I can just bring this down, 210. P equals 210. Okay, I have solved for P. That was the question that was asked. Now, again, don't just take my word for it. We got to prove these things out. We got to prove these things out. For when we prove, we become enlightened. For when we prove, we know with 100% certainty we are correct. So let's go ahead and substitute this 210 in for p in the original equation. So this is the original equation. Equals, let's see, 185. Perfect, that was the original equation. Let's go ahead and substitute that 210 back in and see if it results in number equals number, statement of truth, and so forth. Okay, so 2 times 210, that happens to result in, let me think about that for a second. Oh, I'm sorry, wait a minute. Am I messing up here? No, 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 I'm right. Okay, wait a minute. Wait a minute, something's not right here. Something's not. Where did I go wrong here? Where did I go wrong? Oh, wait a minute. I apologize, guys. In my, in my, in my conversation about the reciprocal and all that, I sort of lost track and sight of that. Yes, I got rid of it here, but I had to do it to the other side. Oh man, okay, yes, yes, I have to. Whatever you do to one side of the equation, you have to do to both. Yes, I sort of lost sight of that, sort of lost track of that as I was explaining and going through all this, but no worries here, no worries, we're back on track. So 210 times 3, that happens to be, let's see, that happens to be 630, and then I have over 2. Okay, so 630 divided by 2, that happens to result in 315. Okay, we're back on track now. I have, see, that is why if I would have gone through the 210, now that's interesting to see. Let's go back and see that actually, because because this is a really good example as to why we prove things out. Let's see, if I would have stuck with that original 210 that we had, 2 times 210, that would have been 420 over 3 minus 25 equals 185. Let's see. That would have been, let's see, what's 420 divided by 3? Let's see, that would have been, let's see, 30, let's see, let's see, let's see, that would have been 13, that would have been 39. Let's see, that would have been 3, 30, let's see, 3 goes into 30. Let's see, 10 times, let's see, 10 times. It would have been basically, to make a long story short, you would have had some number here uh, that did not equal this number. That is why we prove things. That is why we prove things because you would have seen that. You would have seen them, and when you saw that, you would have been, wait a minute, this number here does not equal this number. Something didn't quite work out. Something's not quite right here. And when you see that, you will know that whatever variable you had was the thing that didn't quite work out right. It wasn't correct. So I'm actually kind of glad I made that mistake now that we talk this through a little bit. For we see the value now in proving stuff out. Again, don't take the word for when you get something solved. Prove it. That is your double check. Anyways, not to harp on that too much more, let's go ahead and put now the 315 that we got. So if I put the 315 that we got, okay, let's see, 2 times 315 happens to be 630, and that is over 3 minus 25 equals 180, 185. Okay, great. Let's see, 630 divided by 3, is that divisible? Well, let's see here. It actually happens to be divisible, and you get 210 when you do that. 210 minus 25. Okay, if I do that, I get a 185, and over here I get a 185. Guys, this is true. This is what we were after from the get-go, and this is what would confirm to us that this 315 is correct. Excellent, guys. We got another word problem here. Okay, it's always good to do these word problems. One, you're going to see them a lot, but two, also, this really gets you thinking at a higher level here, at a deeper level, and really connects mathematics to things you will encounter out in the real world. For math is just not numbers and letters on a screen. Math happens to be real world, just represented as symbols. Anyways, let's see. Let's analyze this here. Okay, so now the store has almost 62. Okay, all right, let's see. Oh, interesting. Okay. All right. So we have a department store. Let's see, they have dresses, and the store now has 60, 62. Let's see here. They have, so that would be now has would be my indication that there's an equal sign. Okay, and there's 62. Okay, and we're talking about dresses here. Where does it mention dresses? It mentions it over here on this side of the equation somewhere, and it says there are 3/5 of dresses. Okay, so 3/5 of dresses. 3/5 of dresses. So I'll say D is dresses. Okay, and then let's see, we originally sold 10, but they were returned. And so now we have that. So now we have it. So it so this one's a little bit, so you got to think about this one a little bit. We had sold 10. They initially were subtracted from our inventory, but because they returned, they were added back into our inventory, our current inventory, which happens to be 62. Therefore, this is plus 10. So here, guys, is our equation for consideration. All right, so let's work it. Let's get D all by itself because that is the question. How many dresses were there originally? How many dresses were there? So let's see. Let's see. 3/5 D plus 10. I'm going to start writing things on this side here. see, minus 10, minus 10. Oops. There we go. Minus, oh, come on. There we go. Perfect. Minus 10. Okay. So 3/5 d equals 52. Let's see. I want to divide by 3/2, which would be the same as multiplying by the inverse, or the reciprocal, sorry. And don't forget this time, you have to do it to both. 5/3. Okay. Both sides of the fraction and both sides of the equation. This all eliminates and becomes simply 1d. This here, 52 times 5, that happens to be 260. And then we have over 3. And this does not, I don't like working with decimals here, so I'm not going to have you work with decimals. Just leave it like this. Just leave it like this for now, right? In a real world well, actually, let me go ahead and tell you what this comes out to be decimal wise, and see how this makes sense here. So let's see, 86. So this becomes 86.67. So in the context of real life and real world, how many dresses were there originally? There were 86 dresses originally. You can't have 0.67 of a dress, 2/3 of a dress. It's not. It's either all or nothing. So so we had originally 86. Okay, but mathematically, I want to leave it like this. For when I prove, I want exact numbers to come out. Fractions are exact numbers. Decimals are approximations. Anyways, let's prove this out, guys. Let's prove this out. So here we go. I'm gonna go ahead and substitute this into my original equation here. 3/5 d plus 10 equals 62. Okay, great. Okay, wonderful. All right, let's see here. Now I'm going to put, this may look a little scary and intimidating, but trust the process. Trust the process. Fractions are scary, but they are certainly manageable. All right, so now, again, I'm not even going to look over here until I got this all down to one single value. So let's see here. 3 times 260. 3 times 260 happens to be, let's see, 263, that happens to be 0, 18, and let's see, that's 780. 780, let's see, so 780 over 15 plus 10 equals 62. Okay, so if you do 780 divided by 15, you will end up with 260 over 5. Well, actually you didn't really. You could have actually seen that up front here. These would cancel. These would cancel. You would have 260 over 5. Let me go ahead and, for the interest of space, let me go ahead and do that. 260 over 5. Okay, great. And let's see. 5 divided by 260 happens to be. If I do that right, I get 52. 52. Okay. So 52. 52 plus 10 equals whatever that is. Now let's see, I got one more thing to do for this to become a single value here. 62 is what it is now. This is 62. 62. Hey guys, guess what? 62 does equal 62. It's true. Therefore, all that work, I know, scary fraction. Yikes. All that work though, we got a statement of truth out of it. Whoa. Okay, I don't know what just happened there. There we go. We got a statement of truth as a result of our input. Our input being d is 260 over 3. Therefore, to answer the question, how many were there originally when I had the decimal up there, 86.67, that 86 would be the answer. Putting it into real world context, I left it in fractional form because I wanted to get my proof to result in exact numbers. Therefore, there we go. All right, another word problem, guys. Again, we have to be really good at these. Really good. Really good. For this is real life. This is the real life connection with mathematics. All right, so let's analyze this here. How many pages does the bookstore have? How many pages does the bookstore have? Okay, great. Let's see. Let's see. He read a graphic novel. Monday he read this many more pages. More pages would indicate plus, so plus 22. Okay, let's see. If he has read a total, it doesn't say the word a total, but it is implied. If he has read a total of 220, so total implies not only addition on this side between stuff, but it also implies equal sign. So equals 220. Okay, and then let's see, this thing here, what is that thing? Let's see, where's my variable? Let's see, novel. Novels have pages. Novels have pages. So I can say 3/4 of the pages. 3/4 of the pages. So there you go. There you go. That is the equation from which we will now work off of. So let me rewrite over here. It's the 3/4 p, not equals, but plus 22 equals 220. So let's start inversing this thing. Inversing this thing with the idea that we are achieving balance by eliminating stuff from one side and transferring it to the other. So this still is 3/4 p. This equals, let's see, this happens to be 198. 198, there we go. Divide 3/4, or in other words, reciprocal this thing, and when we do, these cancel. Don't forget, you must do it to both sides of the equation. Let's see, so now I'm left with p equals, let's see, what's 198 times 4? What is 198 times 4, guys? Let's think about that for a second. Trying to do some mental math here, but okay. I think it is 792 divided by, oh wait, not 3, 4, or, no, yeah, 3. Anyways, there I go. This is not divisible. Actually, wait a minute. Yes, it is. Wait a minute. I can divide that by 3. Let's see, 792 divided by 3 happens to be 264. Is it though? Is it though? Let's see if I made a mistake here. Let's see, let's prove. For when we prove, we vet out possible mistakes. So 3/4 plus 22 equals 220. 220. Okay, let's do that. Let's 264. Okay, wonderful. Okay, so let's see. 3 times 264, that happens to be 792 divided by 4 plus 22 equals 220. Let's see. 792 divided by 4, that happens to be 198 plus 22. And you see, add these two up here, you end up getting 220. 220 does, in fact, equal 220. We proved it, guys. We proved it. We proved it. Great, great, excellent stuff, guys. Excellent stuff. So let's switch gears just a little bit here. I know that we've been spending a lot of time solving equations involving more than one operation. That is one of the targets of learning for today. It's not the only one, though. We got to talk about consecutive integers here for a second. So let's do that. Let's do that here. Okay, so as I said, consecutive integers. Now, it would be very helpful to recognize what the word itself, consecutive, means. This isn't strictly a mathematical term. This is a term used in all sorts of aspects of life and other classes and such. Consecutive timelines, consecutive, things. But basically, what if you understand that, then you would understand what consecutive integers are. And consecutive integers are simply integers in counting order, such as 4, 5, and 6. 4, 5, and 6, they are indeed in order. And so I've sort of deemed this term here, but there are many real world applications for what I call variabilizing. Variabilizing. the counting process. So instead of 4, 5, and 6, if I wanted to variabilize it, I would, maybe say where I'm going to start from. Maybe that would be my initial variable. So I can say maybe that's n, and then the next one away from n in order would be n plus 1, and then n plus 2, right? 2 away from the original, 1, 2 there. Okay, so variabilizing the counting process. So instead of saying all that, again, I will reiterate here, it would be n and n plus 1 and n plus 2, right? Where if I substituted n to be 4, and this would be 4 plus 1, and this would be 4 plus 2, I would get 4, and then 5, and then 6, just like I had before. So, oh, and here I go. When n equals 4, the sequence is maintained. In this variabilized form, now we have the ability to execute correct, repeatable, provable counting algorithms for all sorts of real-world applications. Computers they have these things billions of times over, hundreds of thousands of times over in your phones, in your PCs, in any sort of real technology involving computers, right? These things called loops, these things, we don't always know where we want to start counting from, but it doesn't necessarily matter if we don't know it up front. We'll figure out where we're starting from later, but have the general structure, have the skeleton in place so that when we do figure out where we're starting from, we can maintain that counting sequence, that counting, uh, you know, maintain it basically, keep it, going. So that's the idea. Now, this may seem a little abstract to you at this point in time. No worries. I'll do an example or two, okay, and we'll figure this out here. Again, it's this occurs all across real world scenarios, especially when dealing with computers, computer programming, anything like that. This is where they pop up so much. So with that said, here's sort of a little reference table here that I'll make brief mention of as we go through. But there's really three types of consecutive integers. There's one where they're one right after the other, just plain old consecutive. I call this standard consecutive integers, right? They just come in order, right? And the next one over, and the next one over there. Then you have these things where, consecutive even integers, consecutive odd, where, if you were to list out odd numbers, for example, you'll notice 1, 3, 5, 7, and on and on and on. They skip 2. They skip 2 each time, right? So 3 minus 1 is 2. 5 minus 3 is 2. 7 minus 5 is 2. They skip 2 each time they go, whereas when we had 4, 5, and 6, they skipped only 1. And therefore, this plus increased by 1 each time. So to maintain, when you have a consecutive even, and even an odd one, it skips by 2 each time, right? So keep that in mind here. Again, very abstract, I know at this point in time. It's okay. It'll become much more clear when we do an example here right now, in fact. So here we go. Here we got our first example here. So this is a consecutive odd integer problem. And I said just a second ago, odd numbers, examples of them being 1, 3, 5, 7, where they skip by 2 each time. So keep that in mind here. So kind of sort of a word problem here. Find 3 consecutive odd integers with a sum of, so we now know that when we do word problems, right, we have, uh, with the sum of such and such. So the sum of, actually I'll maybe leave a lot more space here. Okay, the sum of, so I know there's going to be some addition happening here, equals negative 51. Now, what exactly am I summing? What am I adding together? Well, I'm adding 3 things together, 3 consecutive odd integers. Now it doesn't, this is all the problem tells me. It doesn't exactly tell me what they are. I don't know where we're starting from in our counting process, but it's okay. I don't need to know in order to build out an algorithm, a skeleton, something to get us going here. I don't need to know it, but I can variabilize the idea that I have three separate things that are going to be in order. So I can variabilize. I can say I'm going to start wherever it is I start from. It is what it is. And then let's see if I'm doing in order odd integers, then I would have here a n plus 2, and I would have here an n plus 4 in accordance with this table up here, right? Skipping by twos, right? Anyways, now this may seem a little ugly, maybe daunting, who knows? But the idea, or not the idea, but like in math, you know that you can rearrange some things here. So let me try to make this a little less daunting by rearranging the terms. You can do that through the associative, or not, sorry, not associative, the commutative properties of addition, subtraction, multiplication, and so forth. You can rearrange through that fundamental property. So let me rearrange some things here. N, I got an N here, I got another N here, and I got another N here. Or sorry, I got three N's total. Okay, so let me just rearrange here. I got that. I also have some numbers here. I have a 2 and I have a 4, and that equals negative 51. Okay, well now we know now that we can basically combine like terms. These are all like terms. We can combine them. So now I have three of these things, and these have no associated variable. So I can combine those. Now I have negative 51. Now this looks a little bit more sort of what we did earlier with our multi-step equations. This looks a little more manageable, a little more solvable, you would say. So let's go ahead and try that. Let's solve that thing. Minus 6 minus 6. I got 3n equals, put equals, let's see, minus 57, divide 3, divide 3, n happens to equal negative 19. Aha, now I solve for n. Now though, understand the question is not asking me to solve for n, it is asking me to solve for three consecutive integers. So let's think about this here for a second. If I have n, and I just said it was negative 19, okay, and then I have, let's see, I had n plus 2, and then I had n plus 4. So let's see, negative 19 plus 2 would be negative 17. Let's see, negative 19 plus 4 would be negative 15. These are all in a row. This is what the question is asking. What are those three integers? This is what the question is asking. So don't stop when you just get an n, right? You know, recognize what the question is asking. So there's that. But don't just take my word for it, guys. We have to prove it. We have to prove it, and we do so by substituting these back in to the original equation. So I had an n, let's see, I had plus, okay, n plus 2, and then I had that equals negative 51. All right, so go ahead, substitute back in, negative 19 plus 2, negative 19 plus 4, okay, got that. So let's see here. Let's see, this becomes negative 17, this becomes negative 15 equals negative 51. So if I subtract all of these together, I end up with negative 51. And in fact, negative 51 does in fact equal negative 51. So you see, guys, even though I was given very little information to start with, I didn't know where I started with actually. I had to figure that out. I did figure it out, but once I figured it out, so where I started with the algorithm, the skeleton held true. Therefore, this n was in fact proven true. This n is in fact equal to -19, and therefore the rest of the sequence is -19, -17, -15. Excellent, guys. I know, again, very abstract. It's all over in the real world, though. And it's not too bad. It just seems not as intuitive if you've never been exposed to it before. But let's do one more just to make sure we really got this one. Okay. All right. So I won't throw odd at you. I won't throw even at you. I'll just throw standard consecutive at you. All right. Three consecutive. Consecutive. There's just so standard consecutive. So n and n plus 1 and n plus 2. And actually, you know what? Equals 21. That is the equation right there. That is the equation. I know it's misspelled here. Sorry. That is the equation. So let's go ahead and put it together, man. So n plus n plus 1 plus n plus 2 equals 21. Okay, again, there's three of them. So I have three representations of integers in consecutive order. Consecutive meaning one right after the other. So I have a 1, and then a 2 is right after that 1, and so forth. They're one right after the other. In fact, you could even consider this to be 0 if you really want. So 0, 1, 2. They're all one right after the other. Anyways, so here we go. If I rearrange some things here, then you will see that I can combine these to be 3n, and I can combine these to be plus 3, and that's 21. And so now I can start inversing. So let's inverse. Let's inverse this. 3n equals, let's see, this happens to be, what is this? 18. 18. So 3, 3. Okay, nice. So n equals 18 over 3. Now I know what you're thinking. Hey, wait a minute. 18 over 3, that's a rational number. A rational number is not an integer. And yes, that's true. It is not. Actually, wait a minute. I apologize. I don't know what I was thinking. Of course, 18 is divisible by 3. What am I saying here? Whoa, I apologize here. Yes, it is 6. It is an integer. Okay, there we go. Okay, but we're not done. We're not done. As again, we're not being asked to solve for n. We're being asked to solve for the three integers that appear in succession. So if this is 6, then 6 plus 1 would be 7, and 6 plus 2 would be 8, and these do appear to be in succession, one right after the other. Let's prove this thing. Is our hypothesis correct, though? Let's see here. Let's see, I got my 3 equals 21. Okay, I got my 3 there. So I had 6, I had 6 plus 1, and I had 6 plus 2. This happens to be 6, 7, 8 equals 21. There's pluses in between. Okay, if I add all these up, they do in fact equal 21. 21 happens to be true, guys. This is true. This is a true statement. We have determined that the initial starting point, n, was 6, and then we found that the successive integers from there. So we have successfully now solved equations involving more than one operation, and we have also successfully solved equations involving consecutive integers. We have accomplished our objective, guys. So with that said, thank you so much for joining me. I hope to see you on the next one. In the meantime, take care, have a good one, and I will see you here soon. Bye-bye.